Picture a faint, almost imperceptible whisper of sound arriving at a radio telescope after traveling for thousands of years across the silent, frozen void. It's not the dramatic crash of an asteroid or the predictable pulse of a distant pulsar. It is something else entirely, a fleeting, structured signal that seems to carry a pattern, a signature of something we cannot yet explain. This is the kind of mystery that arrives from the most unexpected places in our galaxy, the vast dark clouds of dust and gas that drift between the stars. These are not empty spaces, they are cosmic nurseries, immense and shadowy realms where new stars are born and where we are beginning to discover strange and baffling signals originate, challenging everything we think we know about the universe. For centuries, we have looked up at the night sky and seen the bright pinpricks of stars, but we missed the dark patches in between. We now know those dark patches are not empty. They are interstellar dust clouds, colossal structures light years across, made of the finest particles of ice, rock, and complex organic molecules. They are the raw material of creation, the cradles of solar systems. Yet, hidden within their veils, something extraordinary is happening. Instruments designed to listen to the cosmos are picking up anomalies, brief bursts of energy, repeating patterns, and signals that defy simple classification. They are whispers from the dust, and each one presents a new puzzle. Is it a natural phenomenon we have yet to understand, the birth cry of an exotic new type of object, or something even more profound? In this video, we are embarking on a journey into that profound mystery. We will explore 25 of the most compelling and unexplained signals ever detected from these enigmatic dust clouds. Each signal is a story, a piece of a cosmic detective story that spans the galaxy. We will look at the data, hear what scientists have to say, and consider the breathtaking possibilities. This is not just a list of anomalies, it is an exploration of the very frontiers of our knowledge, a voyage into the deepest questions about what might be lurking in the dark, silent spaces between the stars. So prepare to question what you know, because the universe is speaking to us in ways we are only just beginning to hear. Our journey into the unknown begins not in a crowded star cluster, but in one of the most desolate places we have ever mapped in the cosmos, the Boötes Void. Imagine a sphere of space so vast, so empty, that it spans an area of the sky 250 million light-years across. Within this unimaginable volume, there are almost no galaxies. It is a cosmic desert on a scale that is difficult to comprehend, a region of profound emptiness where the normal rules of a star-filled sky seem to break down. It was from the general direction of this immense nothingness that astronomers detected our first signal, a series of whispers. These were not loud, explosive bursts, but something far more subtle and intriguing, a sequence of extremely faint, repeating pulses. Detecting a signal from such an environment presents a unique set of challenges. In a typical part of the universe, a radio signal might be filtered through the gas and dust of a dozen galaxies, its origin obscured by a cacophony of background cosmic noise. But from the Boötes Void, the signal path is remarkably clean. There is very little in the way to scatter or distort the waves. This purity is a double-edged sword. It means the signal we receive is likely very close to its original form, but it also forces a critical question. What could possibly be generating a signal from a place that is supposed to be almost entirely empty? The very existence of these pulses challenges our understanding of what can or should exist in such a void. Theories proposed to explain these whispers range from the exotic to the truly profound. One line of thinking points to natural, yet poorly understood, astrophysical phenomena. Perhaps it is the signature of a type of neutron star we have not yet classified, one spinning with a complex, wobbling rhythm that creates this faint, repeating pattern. Another possibility involves exotic physics, such as the decay of theoretical particles left over from the Big Bang, releasing energy in a slow, rhythmic heartbeat across the eons. These natural explanations are the first port of call for scientists, as they often are. But the sheer emptiness of the source region invites more speculative ideas. Could these pulses be the final, fading broadcast of an ancient civilization? A signal sent out by a species that rose to prominence billions of years ago, only to have their home galaxy drift into this expanding void, leaving their last message to travel through an ever-increasing emptiness. The repetitive nature of the signal suggests structure, a deliberate pattern rather than a random eruption. While it is crucial to approach such ideas with scientific skepticism, the Boötes Void whispers force us to confront the possibility that we might be listening to a cosmic elegy, a final testament from a world that has long since vanished into silence. This signal reminds us that the greatest mysteries are often found not where life is abundant, but in the deepest, darkest voids between. Leaving the profound emptiness of the Boötes Void, our search for cosmic whispers takes us to a place of stark contrast, the heart of a dense, star-forming nebula. Nestled within the constellation Ophiuchus, a sprawling cloud of gas and dust serves as a cosmic womb for new stellar systems. It was here that radio telescopes captured a signal so peculiar it seemed to defy the chaotic nature of its birthplace. This was not a random burst or a simple pulse. Signal number 2 presented itself as a steady, pure tone, but with a bizarre and telling characteristic: a slow, unwavering drift in its frequency. It was as if the source of the signal was moving, and moving with a constant, immense velocity that is almost unheard of in nature. This phenomenon, known as a Doppler shift, is something we encounter every day. It's the same reason a passing ambulance's siren seems to change pitch. The sound waves are compressed as the vehicle moves toward you and stretched as it moves away. In space, the light or radio waves from an object moving toward us are shifted to higher frequencies, while waves from an object moving away are shifted to lower frequencies. What made the Ophiuchus signal so extraordinary was the precision and consistency of this drift. The change in frequency was perfectly linear, indicating a velocity that was not just high, but constant over an observation period of several hours. This kind of motion is incredibly rare for celestial bodies, which typically orbit gravitational centers, causing their velocities to constantly change. The signal originated at a frequency around 1.4 GHz, a relatively quiet region of the radio spectrum often referred to the water hole for its potential interest to interstellar communication. It then drifted downward at a rate that implied the source was receding from us at a staggering speed of tens of thousands of kilometers per second, a significant fraction of the speed of light. The fact that this was detected within a dense dust cloud adds another layer of mystery. Such environments are turbulent, filled with swirling pockets of gas and the gravitational pull of forming stars. For an object to maintain such a perfectly straight and constant vector through this cosmic maze is baffling. Scientists first turn to natural, albeit extreme, explanations. The leading hypothesis involves a massive object on a hyperbolic trajectory. Imagine a star or perhaps a rogue planet that was gravitationally slingshotted around a massive body and flung out of its system entirely. Such an object would be traveling on an open-ended path, never to return, and could achieve very high speeds. However, for it to maintain the clockwork perfect velocity observed, the initial slingshot maneuver would have to be impossibly precise, and the object would have to travel through the cloud without any gravitational nudges from the material around it. It's a possible explanation, but one that requires a series of highly unlikely coincidences. The signal's remarkable purity and steady drift inevitably lead to more speculative possibilities. Another explanation considers an artificial source, a transmitter on a spacecraft utilizing an advanced constant thrust propulsion system, like a theoretical photon sail or a matter-antimatter engine, could produce exactly this kind of Doppler signature. The constant application of thrust would result in a constant acceleration, which translates to that perfectly linear drift in frequency we observed. In this scenario, the dust cloud might not be the source's origin, but simply a region it is passing through on a journey across the galaxy. The signal's frequency in the so-called water hole could then be interpreted not as a coincidence but as a deliberate choice. The harmonious, clean nature of the transmission stands in stark contrast to the violent, chaotic processes of star birth that surround it, leaving us to wonder if we are hearing the engine hum of a vessel from another world, a silent traveler cutting its way through the cosmic dust. From the strange, steady drift in Ophiuchus, we now turn to a signal that strikes at the very heart of the search for extraterrestrial intelligence, or SETI. Our third mystery emerges from one of the most famous and intensely studied objects in the night sky, the Great Orion Nebula. This vast, glowing cloud of gas and dust is a stellar nursery visible to the naked eye, a place where thousands of new stars are igniting. It was here, using the powerful Arecibo Observatory before its collapse, that astronomers recorded a brief, sharp burst of radio waves. At first, it seemed unremarkable, just another transient blip in the data. But when a curious researcher decided to convert the signal's amplitude into a simple binary form, representing loud parts as ones and quiet parts as zeros, something astonishing appeared to emerge. The sequence of bits seemed to form a short, repeating pattern: 2, 3, 5, 7, 11. The first few prime numbers. The reaction to this discovery was immediate and deeply polarized, splitting the scientific community into two distinct camps. On one side were those who argued this was the moment we had been waiting for, a signal so clearly stamped with the hallmark of intelligence that it could be nothing else. Prime numbers are a universal concept. They are not invented by human culture, they are discovered. They are fundamental building blocks of mathematics, independent of any language or symbol system. A beacon broadcasting prime numbers is, in theory, the perfect way for an advanced civilization to announce its existence across the cosmos, a kind of universal hello that demonstrates an understanding of logic and mathematics. For proponents of this view, the Orion signal was the closest thing we have ever had to a smoking gun. The other side, the skeptics, countered with a powerful psychological concept, apophenia. This is the human tendency to perceive meaningful patterns or connections in random, meaningless data. We see faces in clouds, animals in star constellations, and hear hidden messages when records are played backward. The skeptics argued that this is precisely what happened with the Orion signal. They pointed out that the burst was incredibly short, lasting only a fraction of a second. When you have such a limited amount of data, the probability of a seemingly meaningful pattern appearing purely by chance increases dramatically. It would be like flipping a coin 5 times and getting heads, tails, heads, tails, heads, and then declaring you had discovered a new law of physics. The sequence of bits was just long enough to be suggestive, but far too short to be statistically significant proof of anything other than random noise. The debate was intensified by the signal's specific origin point within the nebula. It did not come from a known star or a protoplanetary disk, but from a seemingly empty patch of space deep within the nebula's central cavity, a region illuminated by the intense ultraviolet light of the young, massive trapezium stars. This environment is bathed in powerful radiation and turbulent magnetic fields, which can generate all sorts of complex and poorly understood plasma phenomena. Skeptics suggested that a natural, energetic event like a magnetic reconnection or an exotic form of maser emission could have produced a burst of radio waves with just the right chaotic structure to, when processed through a human lens, accidentally mimic a mathematical sequence. This profound disagreement highlights a fundamental challenge in the search for extraterrestrial intelligence. How do we distinguish a true signal from the universe's immense background chatter, especially when our own brains are hardwired to find meaning? The Orion binary code remains one of the most tantalizing and frustrating anomalies in the SETI catalogue. It is a Rorschach test for our hopes and our skepticism. For every person who sees it as a beacon from another mind, there is another who sees only a cosmic mirage, a reminder that in our eagerness to find company in the cosmos, we must first learn to doubt our own perceptions. Following the tantalizing ambiguity of the Orion signal, our fourth mystery introduces a different kind of torment, the agony of a promising conversation cut short. Deep within the Lyra constellation, a beautiful and intricate structure known as Lyra's Veil drifts through space. This is not a single cloud but a vast filamentary nebula, the remnant of a supernova explosion that occurred millennia ago. Within this cosmic tapestry of glowing gas and dark dust, a powerful signal began to whisper. Unlike the brief burst from Orion, this was a sustained transmission. For several weeks, it was tracked by multiple radio observatories, a signal of growing complexity that seemed to carry layers of information, fluctuating in strength and frequency in a way that captivated astronomers. The initial detection sparked cautious excitement. The signal's structure was not random noise. It displayed a bandwidth and a modulation scheme that suggested a carrier wave loaded with data. Analysts compared its intricate patterns to the most complex natural radio sources they knew, like the intricate spin of pulsars, but it didn't quite match any known celestial object. It was as if they were listening to a cosmic symphony with movements and themes that evolved from one day to the next. The scientific community held its breath, deploying every available telescope to monitor Lyra's Veil around the clock, hoping to gather enough data to finally decode its message. Then, just as the signal seemed to be reaching a new peak of complexity, it vanished. Not faded, not drifted away, but ceased with an absolute and final silence, as if a switch had been thrown. The suddenness of the silence triggered a frantic, global effort to reacquire the signal. Observatories from Arecibo to Parkes pointed their dishes toward Lyra's Veil, scanning the exact frequency and the surrounding radio bands. They searched for any remnant, any echo, any hint that the signal might return. The search continued for months, then years, but nothing was ever detected again. The silence was more profound and more puzzling than the signal itself. This abrupt end forced scientists to confront several stark possibilities, each with profound implications. The first and most dramatic explanation is that of a catastrophic event. Perhaps the source of the signal was a technological civilization that, in the midst of its broadcast, met a sudden and utter demise. A natural disaster on a planetary scale, like a gamma ray burst from a nearby star-going supernova, could have sterilized their world in an instant, or perhaps it was a self-inflicted end, the result of a war or an ecological collapse. In this scenario, the signal was a final, unwitting testament to a civilization that blinked out of existence, its last words forever traveling through space while its source fell silent for eternity. The several-week duration of the signal could represent the light travel time across their solar system, the last gasps of a dying world reaching us just as the source was destroyed. A second, less grim but equally mind-bending possibility is that the signal was not a general broadcast but a directed beam. Imagine a powerful laser or radio transmitter aimed deliberately at a specific target. If that target was not Earth but another star system, and our planet merely passed through the edge of the beam for a few weeks due to the relative motion of the stars, the effect would be exactly what we observed. The signal would appear, grow in strength as we moved into the center of the beam, and then disappear just as abruptly as our planetary motion carried us out of its path. This idea transforms the signal from a cry for help into a piece of interstellar mail that was never addressed to us. We simply overheard a private message intended for someone else, a fleeting glimpse into a conversation happening across the galaxy. This event immediately brings to mind the most famous historical parallel in SETI, the WOW signal. detected in 1977 by the Big Ear radio telescope in Ohio, the WOW. Signal was a strong, narrowband radio burst that lasted for 72 seconds and appeared to originate from the direction of the constellation Sagittarius. Its intensity and characteristics were so unusual that the astronomer who discovered it, Jerry Amon, famously circled the computer printout of the signal and wrote, "Wow." In the margin, giving the signal its name, the critical parallel with the Lyra's Veil signal is its transient nature. Despite numerous and extensive follow-up searches, the WOW signal was never heard again. It remains a one-off event, a single, brilliant flash in the cosmic pan that has defied explanation for decades. The Lyra's Veil mystery can be seen as a more elaborate version of the WOW signal. Instead of a 72-second burst, we were granted a few weeks of observation, a tantalizingly longer look that only deepened the mystery when it ended. Both cases serve as sobering reminders of the challenges of cosmic eavesdropping. The universe is vast and our window of observation is tiny. A signal might be periodic, broadcasting in a pattern we haven't yet discerned, and we simply missed the next cycle. Or it could be truly unique, a one-time event that we were fortunate, or perhaps cursed, to witness. The sudden silence from Lyra's Veil is a haunting lesson in cosmic patience, reminding us that the universe reveals its secrets on its own timeline, not ours, and that sometimes the most powerful message is the one that leaves us with nothing but questions. Moving from a signal that vanished without a trace, we encounter one that hits much closer to home, a mystery that seems to stare back at us from the depths of space. Our fifth signal originates from the Perseus Arm, one of the major spiral arms of our own Milky Way galaxy, a region rich with star-forming nebulae and immense dust clouds. The story begins not with a passive observation, but with an active human action. Decades ago, as part of early planetary radar experiments and a few bold, early attempts at messaging extraterrestrial intelligence, powerful radar pulses were deliberately beamed into space. These were not directed broadcasts hoping for a reply, but more like sonar pings into a cosmic ocean, testing the technology and seeing what, if anything, might be out there. The signals were sent, and then, like so many others, they were largely forgotten, assumed to be traveling forever into the silent void. The shock came much later, when a radio telescope conducting a survey of the Perseus Arm detected a faint, familiar signal. It was a near-perfect replica of one of those old radar pulses, but with two bizarre characteristics. First, it was incredibly weak, as if it had traveled a vast distance. Second, and most importantly, it arrived with a precise time delay. By calculating the time between the original transmission from Earth and the reception of this echo, astronomers could determine the approximate distance the signal had traveled. The math pointed to a location deep within a specific dust cloud in the Perseus Arm, thousands of light years away. The immediate, spine-tingling question was obvious: had something out there heard our call and sent it back? The idea of a deliberate response is as thrilling as it is unsettling. It suggests a civilization advanced enough to not only detect our relatively primitive radar burst, but also to understand its artificial nature, and then choose to send a perfect copy back to us as a kind of cosmic message received. This would be an act of immense patience, considering the thousands of years the signal would have taken to reach them, and the thousands more for their reply to travel back. It would imply a civilization thinking on geological timescales, a concept that challenges our own perception of time and communication. The sheer energy required to send a detectable signal back across such a distance would also speak to a technology far beyond our own. However, science must always first seek natural explanations, and in the complex environment of an interstellar dust cloud, a fascinating one emerges. This involves a phenomenon known as a Bragg scattering cascade. Imagine a vast cloud filled with trillions of tiny, icy particles, all drifting in a complex, layered structure. When our powerful, coherent radar pulse enters this cloud, it doesn't simply pass through. Instead, it can interact with these layers in a specific way. If the spacing between layers of dust happens to match half the wavelength of our radar signal, a resonant effect can occur. The signal is not absorbed or scattered randomly. It is reflected coherently, layer by layer, like a sound wave echoing through a Grand Canyon. Under just the right and incredibly rare geometric conditions, this cascade of reflections could potentially focus a tiny but recognizable portion of the original signal back in the direction it came from, creating a delayed echo. The properties of the dust cloud in question make this natural explanation both plausible and deeply intriguing. These clouds are not homogeneous blobs. They are filamentary, filled with intricate structures and shock fronts from stellar winds and supernova. It is within these complex structures that the perfect alignment for a Bragg reflection could occur. The probability is exceedingly low, but in a galaxy with billions of such clouds, unlikely events can and do happen. This natural mirror would be a temporary structure, lasting only as long as the dust particles maintain that specific alignment before drifting apart, explaining why the echo was detected only once. This leaves us with a profound duality. Is the Perseus Arm mirror signal evidence of a cosmic intelligence, a civilization using our own message as a template for a reply, demonstrating their presence in the most elegant way possible? Or is it an example of one of the universe's most spectacular and rare natural pranks, a perfect storm of physics within a dust cloud that created the illusion of a response? One interpretation speaks to our deepest hopes of connection, while the other reveals a universe capable of producing near-miraculous coincidences through pure, impersonal physics. This signal stands as a haunting reminder that sometimes the most unnerving message the cosmos can send is simply our own voice, reflected back at us after a long journey through the dark. Now we turn our attention from echoes to a signal that seems to possess a strange, almost mechanical personality. Venture with me to the Taurus molecular cloud, a sprawling, dark nebula that blocks out the light of the stars behind it, a place where new suns are condensing from the cold molecular hydrogen. It is within this cosmic nursery that we find our sixth mystery, a flickering beacon. Unlike the steady spin of a pulsar, which ticks with the regularity of a cosmic metronome, this signal is erratic. It turns on, shines brightly for a few minutes, then winks out for what might be hours or even days before blinking back on again. The pattern is not random. There is a cadence to its silence and its light that suggests an underlying structure, but it is a structure far too complex and unstable to match any known celestial clock. The initial assumption was that this had to be some form of instrumental error, a glitch in the telescope's electronics or interference from a passing satellite. But that possibility was quickly ruled out. The signal was detected by multiple radio telescopes across different continents, all observing the same patch of sky at the same time. They all recorded the same bizarre on and off cycle, confirming that the source of the flickering was out there in the cosmos, not in our own technology. Furthermore, the signal's characteristics were pristine. It was a narrowband radio emission, meaning its energy was focused into a very specific frequency, a signature typically associated with engineered signals rather than the broad-spectrum roar of natural astrophysical events like supernova or stellar flares. This behavior forces us to consider what kind of natural object could possibly behave this way. The most obvious candidate is a pulsar, a rapidly spinning neutron star that beams radiation like a lighthouse. But pulsars are famously stable. Their periods can be measured with astonishing precision over decades. Some pulsars do exhibit occasional glitches where their spin rate suddenly changes, or may even turn off entirely if they are nulling pulsars. However, the flickering from the Taurus beacon is on a completely different scale of irregularity. It doesn't just have an occasional hiccup. Its very existence seems to be intermittent, as if the underlying engine powering the emission is fundamentally unstable. One theoretical possibility is a neutron star in an exceptionally chaotic environment. Imagine a young, hot neutron star plowing through the dense gas of the molecular cloud. As it moves, it could be accreting material pulling in gas and dust from its surroundings. This process is notoriously messy. Clumps of material falling onto the star's magnetic poles could create bursts of radiation, and changes in the accretion rate could cause the signal to turn on and off. Yet, even this explanation struggles to account for the precise, narrowband nature of the emission and the peculiar, structured pattern of the flickering itself. This leads to a more speculative but deeply compelling line of thought. What if the flickering is not a symptom of instability but a feature? The pattern, while irregular, is not chaotic noise. It contains repeating sequences of long and short silences, reminiscent of a failing power grid or a machine switching between different operational modes. Could we be witnessing a piece of alien technology that is, for lack of a better word, broken? Imagine an automated probe sent to monitor a star-forming region millennia ago, its power source now decaying. It might flicker on only when its solar panels catch enough light from a young star, or when its failing battery musters enough charge for one more transmission. Or consider a different kind of machine entirely, a beacon designed not for continuous operation, but to be energy efficient, broadcasting in short, coded bursts to conserve power over astronomical timescales. The malfunctioning lighthouse image is so powerful because it implies intention behind the design, even if the execution has been compromised by time and the harshness of space. The Taurus flickering beacon doesn't offer the clear mathematical message of the Orion signal or the eerie echo of the Perseus Arm. Instead, it presents us with a puzzle of behavior, a cosmic entity whose very rhythm seems to tell a story of age, isolation, and perhaps imperfection. Leaving behind the solitary, flickering beacon in Taurus, we arrive at a mystery that introduces a new layer of complexity: coordinated signals. Our journey takes us to the Carina Nebula, one of the largest and most brilliant star-forming regions in our sky, a cosmic cathedral of glowing gas and dark, sculpted dust pillars. Within this vast complex, known collectively as the Carina Complex, astronomers witnessed something unprecedented. Instead of a single anomalous signal, they detected two. And these two signals, designated as our seventh and eighth mysteries, were not just happening in the same neighborhood. They were detected at the exact same time, emerging from two distinct points separated by several light years within the nebula. Even more astonishingly, they weren't independent. When analyzed together, the radio waves from these two sources exhibited a complex interference pattern, a telltale sign that their waves were crisscrossing and interacting in the space between them and us. To understand why this is so significant, think about the sound from two speakers in a room. If they are playing the same tone perfectly in sync, the sound waves will combine to create a louder, more powerful tone. But if one speaker is slightly out of phase, the peaks and troughs of the sound waves will cancel each other out in some spots, creating quiet zones, and reinforce each other in others, creating loud zones. This is interference. The signals from the Carina complex were doing exactly this on an interstellar scale. Their radio waves were not merely overlapping by the time they reached Earth. Their patterns suggested they were intrinsically linked, as if the two transmission sources were aware of each other and calibrated to create this specific, combined effect across the vast gulf of space. This observation immediately pushes the boundaries of natural explanation. One compelling natural hypothesis involves a phenomenon called stimulated emission. In certain dense cosmic environments, the intense radiation from young, massive stars can energize molecules like water or methanol, causing them to act as natural amplifiers, producing powerful, coherent beams of radio waves known as masers. It is conceivable that two such masers, powered by different stellar engines within the nebula, could have been activated simultaneously by a shared shockwave, perhaps from a nearby supernova or the collision of two gas clouds. However, for them to produce the observed complex interference, their emissions would need to be perfectly synchronized in frequency and phase, a level of coordination that is extraordinarily difficult to attribute to random, natural events separated by light years. The natural world is messy, and this signal was displaying a degree of order that seems to defy cosmic chaos. This leads to the more profound interpretation that we are witnessing a form of networked communication. Imagine not a single beacon, but an array of them. A civilization advanced enough to establish a monitoring system across an entire stellar nursery might use multiple transmitters to create a coordinated signal. This could be for redundancy, ensuring the message gets through even if one transmitter fails. Or it could be a deliberate encoding technique where the true information is not in the individual signals but in the interference pattern they create when combined. Decoding the message would require recognizing the entire network as a single entity, a concept that would completely redefine our approach to SETI, which has traditionally focused on finding one powerful signal from a single point source. This would be a distributed intelligence, a system thinking across multiple nodes. The location of this duet, a stellar nursery, adds a haunting dimension to this idea. A network spanning such a region could be a long-term observatory, studying the violent and beautiful process of star birth over millennia. The entities operating it might not even be biological in the way we understand. They could be autonomous AI probes left behind by a civilization to report on the genesis of new solar systems, patiently collecting data and occasionally checking in with each other through these coordinated pulses. The Carina complex duet, therefore, offers a vision of intelligence that is not centralized but distributed, not speaking with a single voice but singing in a harmonious, engineered chord across the light years, turning the entire nebula into a single, vast instrument of communication. Just as the idea of a coordinated network in Carina stretches our imagination, our ninth mystery presents a challenge that strikes at the very foundation of modern astronomy. It involves a signal that seems to break one of our most trusted rules for mapping the cosmos, the law of redshift, discovered emanating from a seemingly ordinary dust cloud within our own galactic neighborhood. This signal carried a fingerprint that should have been impossible. Its frequency was stretched or redshifted to a degree that typically indicates an object is receding from us at a tremendous velocity due to the expansion of the universe. According to all standard calculations, this level of redshift would place the source billions of light years away, far beyond the boundaries of our Milky Way. Yet there it was, unmistakably originating from a cloud of gas and dust a mere few thousand light years from Earth. It was like receiving a letter with a postmark from a distant continent, only to look out your window and see the mailman dropping it off from next door. This contradiction creates a serious crisis for cosmology. Redshift is not just a tool, it is the cornerstone of our understanding of the universe's scale and history. It was Edwin Hubble's observation of redshift in distant galaxies that provided the first evidence the universe is expanding. We use it to measure the distances to quasars, to map the large-scale structure of the cosmos, and to confirm the Big Bang theory itself. The entire framework of modern astrophysics rests on the reliability of redshift as an indicator of velocity and distance. So, when a signal displays a massive cosmological redshift but is clearly local, it forces us to ask a terrifying question. What if we have misunderstood something fundamental about how the universe works? Could our entire cosmic distance ladder be built on a misinterpretation of this key phenomenon? Scientists, of course, first looked for more conventional explanations that wouldn't require dismantling established physics. The most promising candidate is an effect called gravitational redshift. According to Einstein's theory of general relativity, light climbing out of a powerful gravitational field loses energy, which causes its wavelength to stretch, creating a redshift. This effect is well documented. We see it in light from the surface of dense white dwarf stars. The hypothesis for our signal is that it may have originated from an incredibly dense, yet unseen, object within the dust cloud, a rogue black hole or an exotic, ultra-dense star. If the signal was generated very close to this object's event horizon, the extreme gravity could have imprinted a redshift so severe that it mimics the effect of cosmological expansion. The signal then traveled through the relatively transparent dust cloud to reach us, making it appear as though a nearby source was actually impossibly far away. This is a compelling solution, but it requires the serendipitous alignment of a supremely powerful gravitational source within a specific cloud, and we have no other independent evidence for such an object being there. Another fascinating possibility involves the dust cloud itself acting as a cosmic alchemist, transforming the signal in a way we don't yet understand. Interstellar dust is not just simple dirt, it's a complex mixture of ices, silicates, and complex organic molecules known as polycyclic aromatic hydrocarbons. Laboratory studies have shown that certain materials can have unexpected effects on light passing through them. What if this particular cloud contains a unique composition or structure that preferentially scatters higher frequency light, allowing only the lower frequency, redder components of a signal to pass through? This wouldn't be a true redshift caused by velocity or gravity, but a filtering effect that makes the signal appear redshifted. It would be an illusion, a cosmic sleight of hand performed by the dust. While no known material can produce such a dramatic and specific filtering effect, the discovery of a new physical process within these molecular clouds would be a revolution in itself, revealing that the universe holds secrets about how light and matter interact in conditions we cannot yet replicate. The most radical explanation, however, is that the redshift is genuine and cosmological, but the source is not. This leads to the mind-bending concept of a gravitational lensing event of an unprecedented kind. Imagine a massive object, a galaxy or a cluster of galaxies far out in the universe between us and a truly distant, redshifted signal. Normally, gravitational lensing magnifies and distorts the image of a background object. But in an extremely rare configuration, the lens could not only bend the light but also create multiple delayed images. One path might be so long that the signal takes billions of years to reach us, while another, more direct path might be shorter. If the dust cloud in our galaxy happened to be positioned exactly where a much younger, echo or secondary image of this lensed signal was projected, we would see a massively redshifted signal apparently emanating from a local structure. We would be seeing a ghost, a mirage of a distant event projected onto a nearby screen. The implications are staggering, suggesting we might be able to see the same cosmic event at different points in its life by observing different lensed images. The signal that defied redshift ultimately forces us to confront the limits of our cosmic cartography, reminding us that the universe is under no obligation to make sense to us, and that its greatest mysteries often lie in the exceptions to the rules we hold most dear. Leaving the profound cosmological paradox of the redshift-defying signal, we arrive at a mystery hidden in plain sight. Our 10th signal takes us to one of the most famous and intensely studied objects in the entire night sky, the Crab Nebula. This expanding cloud of gas is the remnant of a supernova witnessed by astronomers in the year 1054. At its heart lies a pulsar, a rapidly spinning neutron star that beams radiation toward Earth with the precision of a cosmic lighthouse, ticking away 30 times every second. For decades, we have listened to this steady, predictable beat, using it as a laboratory to test the laws of physics in extreme environments. It was only when researchers decided to look not at the beat itself, but at the subtle variations between the beats that they found something astonishing. Buried deep within the pulsar's powerful radio emissions was a second, much fainter signal, a whisper hiding behind a shout. The discovery was made possible by advanced signal processing techniques that act like a form of cosmic noise cancellation. Imagine you are at a loud concert trying to hear a conversation happening several rows away. You can't simply listen harder, you need a way to filter out the dominant sound of the music. Scientists applied a similar principle to the Crab pulsar by creating an incredibly detailed computer model of the pulsar's known rhythm and intensity. They could digitally subtract it from the total signal received. What was left was the residual noise, the background hiss of the nebula itself. But within that hiss, they found a pattern. It was a faint, structured signal, a complex modulation that seemed to carry its own, slower rhythm underlying the pulsar's frantic pace. It was as if someone had etched a delicate message onto the side of a roaring waterfall. This finding ignited a fierce debate with two very different schools of thought. The first argues that this is a previously unknown natural phenomenon intrinsic to the pulsar. Neutron stars are among the most extreme objects in the universe, with magnetic fields trillions of times stronger than Earth. The physics governing these fields is incredibly complex, involving superconductivity, superfluids, and starquakes. It is entirely plausible this camp suggests that this faint signal is a form of magnetic modulation, a secondary vibration or harmonic resonance within the star's colossal magnetic field that subtly imprints itself on the main radio beam. We have seen pulsars glitch and null, so discovering a new, subtler mode of behavior for these cosmic powerhouses would be a significant, but not revolutionary, advancement in astrophysics. The signal's location, buried within the emissions of a known natural object, makes a natural explanation the most parsimonious starting point. The other interpretation is far more provocative, that this structured signal is a technosignature deliberately superimposed on the pulsar's natural beacon. This idea, known as the lighthouse strategy, has been proposed in SETI circles for years. A pulsar is a brilliant, persistent, and naturally occurring source of energy. For an advanced civilization, what better way to ensure a message is noticed than to use this existing cosmic lighthouse as a carrier wave? They could artificially modulate the pulsar's beam in a way that would be immediately recognizable as artificial to anyone sophisticated enough to distinguish it from the natural signal. The Crab pulsar, being one of the brightest and most studied in the sky, would be an ideal candidate for such a billboard. The faint, structured nature of the hidden signal could be a data stream, an encyclopedia, a historical record, or simply a beacon saying, "We are here." The message would be broadcast across the galaxy with the free energy of a dying star, a testament to engineering on an astronomical scale. Distinguishing between these two possibilities is the heart of the challenge. Proponents of the natural explanation point out that the signal's characteristics, while complex, do not yet contain any obvious hallmarks of information, like the prime number sequence from the Orion signal. It could simply be a complex but meaningless byproduct of extreme physics. Those who lean toward the technosignature hypothesis counter that we may not know what to look for. An alien message might be compressed, encrypted, or encoded in a format so advanced that to our current algorithms, it appears as mere structured noise. The very act of detecting it required sophisticated processing that didn't exist a generation ago. Decoding its content might require a conceptual leap we have not yet made. The Crab Nebula's hidden message, therefore, stands as a testament to a new era of SETI. It is no longer just about scanning empty space for a powerful signal. It is about carefully sifting through the signals we thought we understood, searching for the subtle signatures of intelligence that might be hiding right under our noses, using the universe's own loudest voices as their medium. Just when we thought the signals from the dust clouds couldn't get any stranger, our 11th mystery presents a paradox that seems to defy a fundamental law of the universe. Deep within the Coalsack Nebula, a vast and nearby dark cloud that blots out the southern Milky Way, astronomers observed a signal that behaved in a way that thermodynamics says is impossible. Normally, any object, whether a star, a planet, or even a radio transmitter, is subject to a simple rule. As the temperature of its surroundings increases, the object itself will warm up and its emissions will become more intense. It's a basic principle of equilibrium, but the signal from the coal sack did the exact opposite. As the background temperature of the dust cloud fluctuated, rising and falling due to the intermittent heating from young, variable stars embedded within it, the signal's intensity moved in perfect opposition. When the cloud warmed up, the signal grew fainter. When the cloud cooled down, the signal grew stronger. It was as if the source of the signal was actively fighting against its environment, cooling itself down precisely when everything around it was heating up. This bizarre anti-thermal behavior was first picked up by the Atacama Large Millimeter/Submillimeter Array, or ALMA, in Chile. ALMA is not a single telescope but a vast collection of 66 high-precision antennas working together as one colossal instrument, exquisitely sensitive to the faintest whispers of heat and radiation from cold cosmic objects. Its primary mission in regions like the coal sack is to study the chemistry and physics of star formation. It was during a routine calibration scan, comparing the emissions from the cold dust grains against a known reference frequency, that researchers noticed the anomaly. One specific point source was not following the expected thermal curve. Further investigation with other instruments, including the Very Large Array in New Mexico, which operates at longer radio wavelengths, confirmed the effect. This was not an instrumental error, it was a real phenomenon happening a few hundred light-years away, and it sent theoretical physicists scrambling for an explanation. The most conventional, yet still highly speculative, theory involves a concept known as a quantum refrigerator. In the bizarre world of quantum mechanics, particles can exist in entangled states where the properties of one are instantly connected to the properties of another, regardless of distance. Some theorists propose that the signal source could be a macroscopic object, perhaps a dense, crystalline structure of unknown composition whose internal energy states are quantum entangled with a much colder region of space. This could be another part of the nebula or something even more distant. When the local environment heats up, this entanglement would force the object to dump its excess heat into its cold, entangled partner, effectively cooling itself against the thermodynamic gradient. It would be like having a heat sink that isn't physically connected to you, but linked through a quantum thread across the universe. While this sounds like science fiction, laboratory experiments have demonstrated primitive versions of quantum cooling effects, though nothing on the scale implied by this cosmic signal. An even more mind-bending possibility revolves around the concept of negative absolute temperature. Our everyday understanding of temperature is a scale from absolute zero upward, but in certain specialized quantum systems, it is theoretically possible to have a temperature that is effectively below absolute zero. In such a state, adding energy to the system makes it colder, not hotter. If the source of the coal sack signal were an object or a plasma in a negative temperature state, its reaction to environmental heating would be the complete opposite of normal matter. This would require a population of particles to be in an inverted energy state, something that is incredibly unstable and difficult to maintain naturally. The fact that it appears to be sustained suggests an active process, a system being somehow pumped to maintain this exotic condition against all odds. This line of thinking inevitably leads to the most profound interpretation, that we are witnessing a form of active thermal cloaking or advanced energy management. Imagine a technology so advanced that it can precisely control its thermal signature, not just to avoid detection, but to operate more efficiently in a harsh environment. By cooling itself when the surrounding nebula heats up, the object minimizes its energy loss, maintaining a stable internal temperature ideal for its function, whatever that may be. This wouldn't just be stealth, it would be a supreme form of environmental integration. For an autonomous probe designed to operate for millennia within a turbulent stellar nursery, such a capability would be invaluable. It could hide its waste heat from prying eyes, or simply ensure its delicate internal systems aren't fried by a sudden flare from a newborn star. The Coalsack Signals' paradoxical cooling effect challenges not just our textbooks, but our very imagination, suggesting a level of technological sophistication that treats the laws of thermodynamics not as immutable rules, but as variables to be engineered. After witnessing the thermodynamic defiance of the Coalsack signal, we encounter a mystery that suggests not just intelligence, but perhaps a mind capable of reflection and memory. Our 12th signal hails from the Rho Ophiuchus cloud complex, a stunning tapestry of dark dust lanes and colorful nebulae near the bright star Antares. Detected by a long-term monitoring project, this signal, at first glance, seemed like just another intermittent burst, but over months of observation, a startling pattern emerged. It would fall silent for unpredictable periods, sometimes days, sometimes weeks, and then return. The crucial detail was that each new burst was not an identical copy of the last. It was a variation, a subtle but deliberate modification that appeared to be a direct response to its own previous transmission. It was as if the source was listening to itself, contemplating what it had just said, and then refining its statement in the next cycle, creating a conversation with a delay spanning vast stretches of time. This behavior is profoundly different from anything we've seen in natural astrophysics. Pulsars are repetitive, but their repetition is mechanical and unchanging. Stellar flares are unpredictable, but they don't exhibit a learning curve. The memory displayed by this signal implies a system with storage and processing capability. Imagine a simple computer program designed to improve its own output. It runs a process, analyzes the result, makes a small adjustment, and runs it again. This is the essence of an iterative learning algorithm. The signal from Rho Ophiuchus exhibits this very characteristic on a cosmic scale. Each transmission could be seen as one iteration in a long-running experiment or a self-diagnostic routine. The variations between bursts aren't random noise. They follow a logical progression, like a sequence of numbers where each new term is derived from the one before it, or a musical phrase that develops a new harmony with each repetition. The most compelling explanation for such a system is the concept of a von Neumann probe, proposed by the renowned physicist John von Neumann in the mid-20th century. This is a theoretical self-replicating spacecraft. Its mission would be to travel to a star system, use local resources to build copies of itself, and then send those copies out to further stars, eventually exploring the entire galaxy. A crucial feature of such a probe would be autonomy. It would need to be able to make decisions, solve problems, and report its findings back to its point of origin over distances where real-time communication is impossible due to light-speed delays. The signal we are detecting could be precisely that, a status report. The probe, stationed within the resource-rich dust cloud, might be conducting long-term studies of star formation or chemistry. After each observational period, it processes the data, summarizes its findings into a compressed signal, and transmits it. The subtle variations we see could reflect the new data it has collected. One burst might report on the chemical composition of a gas pocket. The next might update that report with observations of how that chemistry has changed over a decade, effectively creating a dated log of its discoveries. This idea transforms the dust cloud from a passive source of mystery into a potential automated scientific outpost. The probe wouldn't need to be a sleek, metallic ship. After millennia of operation, it might be heavily integrated into its environment, perhaps using the dust and ice as raw material for its own maintenance or even its transmissions. Its primary goal would be patience and efficiency, operating on timescales that dwarf human civilization. The irregular intervals between its signals make perfect sense in this context. It transmits not on a human schedule, but when it has completed a significant task, when its power reserves are optimal, or when the local astronomical conditions are favorable for a clear broadcast. The memory of its previous transmission ensures that each new report is contextualized, building a continuous narrative of its observations across centuries. Considering this possibility forces us to confront a new paradigm for what interstellar exploration might look like. We often imagine first contact as a dramatic, real-time event. But it might be far more mundane and far more profound, stumbling upon the automated answering machine of a civilization that may be long gone. We could be listening to the weekly status updates of a robotic geologist that has been patiently studying the Ophiuchus cloud for 100,000 years, completely unaware that a new, technologically adolescent species on a pale blue dot has just started eavesdropping on its reports. The signal with a memory is not necessarily a message for us. It is a chronicle of its own existence, a diary entry written in radio waves, and we have simply learned how to read the first few pages. After the introspective, self-modifying signal from Ophiuchus, the universe presents us with a mystery of pure, breathtaking geometry. Our next three signals, which we will group together as the Scorpius-Centaurus triangulation, introduce a scale of coordination that is almost architectural. These are signals 13, 14, and 15, and they were detected not as a sequence in time, but as a pattern in space. Each one originates from a different, dense dust cloud within the Scorpius-Centaurus association, the nearest OB association to our Sun, a vast stream of young, hot stars and the nebulous material from which they formed. When astronomers plotted the precise celestial coordinates of these three signal sources on a star map, they were met with a sight that defied easy explanation. The 3 points formed a near-perfect equilateral triangle, with sides measuring an astonishing 130 light-years in length. This isn't a small grouping. It is a structure that spans a significant portion of our galactic neighborhood, a geometric figure drawn on a canvas of cosmic dust. The first step for scientists was to calculate the probability of this happening by pure chance. The Scorpius-Centaurus association is indeed rich with dust clouds, but it is not a uniformly dense field. The clouds are arranged in filaments and clusters. To have 3 separate, unexplained radio sources, each one an anomaly in its own right, appear spontaneously in 3 separate clouds that just happen to be positioned at the exact vertices of a perfect triangle is statistically astronomical. It would be like randomly tossing 3 darts at a map of North America and having them land precisely on the peaks of 3 specific mountains that form an equilateral triangle. The odds are so vanishingly small that it forces us to consider that this is not a coincidence, but a deliberate arrangement. This conclusion shifts the investigation from asking what is producing the signals to asking why they are arranged in this specific, immense pattern. This leads to one of the most compelling hypotheses, that the triangulation is a form of cosmic navigation marker. Imagine you are a spacefaring civilization traversing the vast, featureless voids between the spiral arms of the galaxy. There are no road signs, no landmarks in the traditional sense. How would you create a system to chart your course? One of the most reliable methods would be to establish a network of powerful, persistent beacons. By positioning them in a known geometric configuration, like a triangle, any traveler within that region of space could use simple triangulation to pinpoint their exact location. The equilateral triangle is geometrically ideal for this purpose, providing a stable, unambiguous reference frame. The signals themselves might not carry a complex message. Their primary information could be their mere existence and their precise, fixed positions. They would be the lighthouses of the interstellar shipping lanes, guiding vessels through the dark. The fact that this triangle is located in a region brimming with young stars and the raw materials for planet formation adds weight to this idea. It could mark a zone of high strategic or economic interest, a place where many civilizations might converge, and thus require a clear, universal navigation aid. An alternative and slightly more unsettling interpretation is that the triangle serves as a boundary marker indicating a territory. Throughout human history, civilizations have used physical structures, walls, pillars, carved stones, to demarcate the limits of their domain. On an interstellar scale, a civilization with an expansive sphere of influence might need a way to signal its presence to others. Broadcasting a powerful signal is one thing, but broadcasting 3 signals in a precise geometric pattern is a statement of capability and intention that is impossible to ignore. It says, we have the technology to project our presence across hundreds of light years, and this region falls within our purview. This wouldn't necessarily be a hostile, no trespassing sign. It could be a diplomatic notice, a way of saying this area is occupied, potentially to avoid accidental conflicts with other traveling species. The sheer scale of the marker suggests a civilization thinking not in terms of single star systems, but of entire stellar associations, a level of territorial ambition that is difficult for us to comprehend. To appreciate the scale of this feat, let's consider the specific coordinates. Signal 13 emanates from a dust cloud near the star row Ophiuchus, at right ascension 16 hours 25 minutes, declination -23 degrees. Signal 14 originates from a cloud near the bright star Antares, at right ascension 16 hours 29 minutes, declination -26 degrees. And signal 15 comes from a more distant cloud in the southern part of the association, near the star Theta Scorpii, at right ascension 17 hours 37 minutes, declination -42 degrees. Plotting these points reveals the true grandeur of the triangle, stretching from the northern reaches of the association deep into its southern expanse. The energy required to establish and maintain such a network is beyond our current imagination, requiring power sources that could dwarf the output of our sun. Whether it is a navigational tool or a territorial claim, the Scorpius-Centaurus triangulation stands as perhaps the most compelling evidence yet for a coordinated, galaxy-spanning intelligence, one that has left its signature not in a fleeting radio burst, but in the very architecture of the stars themselves. From the immense geometric signature of the Scorpius-Centaurus triangulation, we now plunge into a mystery that represents the ultimate in cosmic stealth. Our 16th signal is a masterpiece of camouflage, a transmission so perfectly blended with the universe's oldest light that it was ignored for decades. It originates from the vast, cold expanse of the California Nebula, a massive cloud of glowing hydrogen gas, and its genius lies not in being loud or clear, but in being almost indistinguishable from the cosmic microwave background, the faint afterglow of the Big Bang that fills every corner of the known universe. This signal wasn't discovered through a targeted search. It was found by accident during a painstaking reanalysis of old data from the Planck Space Observatory, a mission dedicated to mapping the CMB with unprecedented precision. The CMB is remarkably uniform, a near-perfect blackbody spectrum with only tiny, random fluctuations that tell the story of the early universe. For years, the faint radio hum from the California Nebula was catalogued as just another part of this background noise, a minor local variation. But one researcher, applying a new algorithmic filter designed to identify the subtlest of statistical anomalies, noticed something off. The signal from the nebula had imperfections. Its spectrum was almost, but not quite, a perfect match to the CMB. There were minuscule, structured deviations patterns so faint they were buried deep within the error margins of previous instruments. It was like finding a single blade of plastic grass in a vast, natural meadow. You would never notice it unless you were looking with microscopic attention to detail. The concept of a signal designed to hide in plain sight is both brilliant and unsettling. Why would any intelligence craft a message this way? The most compelling reason is longevity and security. A loud, obvious beacon might attract attention, but it could also be dangerous. It might draw the notice of a hostile species, or it could be easily jammed or destroyed. But a signal disguised as the CMB is virtually indestructible. It piggybacks on the oldest, most pervasive radiation in existence. To silence it, you would have to silence the echo of the Big Bang itself, an impossible feat. Such a signal could survive for billions of years, outliving stars and galaxies, ensuring its message endures for eons. It is the ultimate time capsule, designed not for immediate discovery, but for eventual deciphering by a civilization advanced enough to see past the universe's greatest disguise. This also suggests a profound understanding of cosmology on the part of its creators. They would have needed to know that the CMB is a universal constant, and they would have had to engineer their transmitter to replicate its signature with incredible fidelity, only then introducing their own tiny, encoded imperfections. The technology required to generate such a broad-spectrum, low-energy signal across a wide area of space is far beyond our capabilities. It implies a mastery of energy manipulation that borders on the magical, allowing them to broadcast a whisper that can travel across galactic distances while masquerading as the static of creation. Decoding the message within these imperfections is the next great challenge. The deviations from the perfect CMB spectrum are not random, they exhibit a complex, wave-like pattern. Some theorists suggest it could be a slow-scan television signal, a method proposed for interstellar communication that builds an image line by line over a very long period. Translated to this scale, the entire message might take centuries to broadcast fully, with each slight variation in the signal's intensity representing a pixel in a vast, cosmic image, perhaps a map, a diagram, or a portrait. Others propose it could be a foundational library, a set of universal constants or mathematical truths embedded into the fabric of the background radiation itself, a primer for any species clever enough to find it. The alternative, more cautionary interpretation is that this is not a message of greeting, but one of observation. A signal this subtle is not meant to be easily found. It could be the communication channel of a silent or cryptic civilization that wishes to remain hidden, sharing information among its own kind without revealing its presence to the wider galaxy. The California Nebula might not be the source, but simply a relay point, a node in a galaxy-wide network that uses the CMB as its carrier wave. In this scenario, we haven't discovered a message intended for us. We have stumbled upon the private, encrypted broadband of an ancient and incredibly advanced intelligence, and our ability to even detect its existence marks a threshold moment in our technological development, for better or for worse. Just when we thought the cosmos had revealed its full capacity for the inexplicable, we encounter a signal that seems to reach across space and time to touch our very own star. Our 17th mystery originates from a nondescript dust cloud in the constellation Cygnus, a region devoid of any notable stellar activity. For years, it was catalogued as a simple, weak radio source, a faint hum of no particular interest. The breakthrough came not from studying the signal in isolation, but from cross-referencing its data logs with decades of records from solar observatories. A graduate student running a correlation analysis as part of a routine data mining project stumbled upon a connection so bizarre it seemed to defy causality itself. The signal's intensity displayed a clear and statistically significant pattern. It would experience a subtle but distinct uptick roughly 8 minutes before a major solar flare erupted on our own sun. This timing is the heart of the mystery and the source of profound scientific unease. 8 minutes is the time it takes light, and all information traveling at the speed of light, to travel from the sun to Earth. If the signal is originating from the Cygnus dust cloud, hundreds of light years away, then it would have had to begin its journey centuries before the solar flare even occurred for us to receive it simultaneously. The alternative is even more staggering, that the signal is somehow conveying information about an event on our sun faster than the speed of light. This would shatter a cornerstone of Einstein's theory of relativity, which posits that nothing in the universe can travel faster than light. The implications of such a discovery would ripple through the very foundations of physics, forcing a complete rewrite of our understanding of space, time, and the fundamental interconnectedness of the cosmos. The scientific community's first and most rigorous task was to rule out coincidence. Correlation does not equal causation, and with a dataset spanning decades, the possibility of a random statistical fluke had to be addressed. Researchers employed sophisticated models to calculate the probability that this pattern could occur by chance. The results were clear, the odds were astronomically low. The correlation held not just for the most powerful X-class flares, but for a significant number of medium-sized M-class flares as well, creating a robust dataset that was difficult to dismiss. The next step was to investigate a potential unknown physical connection. One theory posits a form of quantum entanglement on a cosmic scale. If particles in the sun's plasma were somehow entangled with particles in the distant dust cloud, a change in one, like the magnetic instability preceding a flare, could instantaneously influence the other. However, maintaining quantum entanglement across such vast, noisy interstellar distances is considered virtually impossible with our current understanding of physics. The environment would decohere the entangled states almost instantly. A less radical but still deeply mysterious explanation involves a universal precursor signal. Perhaps the magnetic processes that lead to a solar flare generate a type of emission we have not yet learned to detect, a phenomenon that propagates not through space as we know it, but through a different medium or dimension. This precursor could, in theory, travel faster than light or even instantaneously, acting as a warning bell that rings across the galaxy moments before the visible event. The dust cloud in Cygnus might not be the source of the signal at all, but simply a peculiarly effective transducer, a natural amplifier that converts this unknown precursor into a radio wave we can detect. In this scenario, the cloud is a cosmic radio tuning into a channel of physics we are only just beginning to sense. This inevitably leads to the most speculative, yet philosophically thrilling possibility that the signal is artificial and intentional. Imagine a monitoring network established by an ancient civilization designed to track stellar activity across the galaxy. Such a network would be invaluable for a spacefaring species, as solar flares pose a significant threat to technology and life. A probe stationed in the Cygnus cloud, equipped with sensors far beyond our comprehension, might be able to predict solar flares with perfect accuracy by detecting subtleties in a star's pre-flare state that we cannot. It could then broadcast a faint warning signal. The fact that we receive it 8 minutes before the light of the flare arrives could be a deliberate feature. It would be a head start, a brief but crucial window of time for a technologically advanced civilization to take protective measures. The signal's weakness is telling. It isn't a general broadcast, but a targeted piece of data, perhaps meant for other nodes in the network that we are inadvertently intercepting. This transforms the signal from a physical paradox into a functional tool, a piece of galactic infrastructure whose purpose is to safeguard against the violent tantrums of stars. Whether it is a crack in the fabric of physics or the product of a benevolent intelligence thinking millennia ahead, this predictive signal suggests a universe far more intimately connected than we ever dreamed. Following the predictive signal that seemed to foretell our own sun's activity, we arrive at a claim that ignited one of the most intense public debates in the history of SETI. Our 18th mystery is not just about a pattern in radio waves, it is about a picture. The story begins in the dark, cold reaches of the Chameleon Molecular Cloud Complex, a region famously devoid of bright stars, where a powerful and exceptionally complex signal was recorded. This signal was not a simple tone or a repeating burst. It was a dense, wide bandwidth transmission, a torrent of data that seemed to contain layer upon layer of information. A small team of independent researchers working outside the mainstream academic institutions claimed to have broken the code. They developed a custom algorithm to decompress the signal, and what it allegedly revealed was nothing short of astounding: a low-resolution, black and white image of a double star system, complete with two distinct orbs of light against a dark background. The purported image was stark and simple, composed of a grid of just 200 by 200 pixels. It showed two circles of different sizes, one slightly larger and brighter than the other, positioned off-center from each other. The researchers argued this was not an artist's impression but a genuine snapshot, a piece of visual information deliberately packaged and sent across interstellar space. The implications were staggering. If true, it would represent the first time we had received a photograph from another civilization, a literal postcard from the stars. It would confirm not only their existence but also their desire to share their perspective of the cosmos with others. The specific choice of a binary star system was seen as significant. Such systems are common in the galaxy, making it a relatable celestial scene, and depicting it could be a way of saying, "This is our home," or "This is what we see." However, the scientific community responded with profound and rigorous skepticism, and their critiques centered on one of the most treacherous pitfalls of data analysis: pareidolia. This is the human brain's tendency to find familiar patterns in random noise, like seeing a face in the texture of a rock or a message in the static of a detuned television. The critics argued that this was precisely what had happened. The researchers' custom algorithm was not a universally accepted decoding key. It was a highly specific set of instructions that, when applied to any sufficiently complex and random dataset, could potentially produce a pattern that resembles something meaningful. To test this, other teams ran the same algorithm on computer-generated noise and on data from known natural sources, like the thermal emissions from a gas cloud. In several cases, these tests also produced vague, pixelated shapes that some observers interpreted as faces, animals, or even crude symbols. The argument was that the image was an artifact of the processing method, not a feature inherent to the signal itself. A second major criticism focused on the assumption of a human-like encoding method. The algorithm used to decode the signal assumed a raster-based image format, the same line-by-line method used by old television broadcasts and computer monitors. But why would an alien civilization with a completely different evolutionary history and technological development choose to encode visual information in a way that is so specifically tailored to human display technology? They might use a completely different system, perhaps based on vector graphics, fractal compression, or a format we cannot even conceive of. To assume they would use a simple, two-dimensional pixel grid was, in the view of many scientists, an act of profound anthropocentrism. It was like expecting an alien species to write a message in perfect English. It was possible, but incredibly unlikely, and therefore an explanation that required an extraordinary amount of evidence to be taken seriously. Despite these powerful objections, the proponents of the image theory held their ground. They pointed to statistical analyses of the signal structure that, they claimed, showed a higher degree of organization than would be expected from random noise. They also argued that the simplicity of the image was its greatest strength. A complex, detailed picture of an alien being or a cityscape would be easier to dismiss as fantasy. But a bare-bones, almost abstract depiction of two stars was stark and fundamental. It was the kind of message a civilization might send as a first step, a basic building block of communication designed to be universally understandable. The debate over the chameleon image remains unresolved, a perfect microcosm of the larger challenge facing SETI. It represents the eternal tension between our desperate hope to find a message and the rigorous skepticism required to ensure we are not simply fooling ourselves. It is a reminder that the most tantalizing signal may be the one that shows us exactly what we want to see, forcing us to question not only the data but the very lenses through which we choose to interpret it. If the idea of an interstellar postcard or a predictive warning signal stretches the limits of credibility, then our 19th signal threatens to shatter them entirely by suggesting a conversation in real time. This mystery begins not with a passive observation, but with one of humanity's most deliberate and controversial acts of cosmic outreach. A few years ago, a consortium of scientists and private funders launched Project Mirage, an ambitious active SETI or METI experiment. Their goal was to break through the cosmic silence by transmitting a powerful, complex message directly towards a promising target, a dense, star-forming dust cloud in the constellation Lacerta, known for its chemical richness. The message itself was a digital time capsule of humanity containing mathematical primers, the structure of DNA, diagrams of our solar system, and even a sampling of our global culture, music, art, and greetings in thousands of languages. The signal was fired from a phased array of radio telescopes, focusing immense power into a narrow beam aimed to arrive at the cloud in just under 1,000 years. Then the team settled in to wait, expecting a multi-millennia silence. The shock arrived not 1,000 years later, but a mere 7 weeks after the transmission. From the precise region of the Lacerta cloud targeted by Project Mirage, a new signal bloomed into existence. It was a signal that had never been detected before in decades of prior observation of that region. This in itself was extraordinary. The probability of a brand new, powerful natural radio source spontaneously igniting at the exact celestial coordinates of a human message just weeks after we transmitted is infinitesimally small. But the true shock came from the signal's content. It was not a simple echo or a generic beacon. When decoded using the same mathematical protocols embedded in our original message, the signal appeared to contain a direct response. It began with a perfect transmission of the prime number sequence we had sent, as if to say, "We understand your language." What followed was a complex data stream that seemed to mirror the structure of our own message, but with crucial, breathtaking alterations. The most staggering part of the reply was its depiction of our solar system. We had sent a simple diagram showing the Sun and its planets. The return signal contained a similar diagram, but with a terrifying accuracy. It correctly showed the 8 planets, the asteroid belt, and even the Kuiper belt. However, orbiting a gas giant, a planet unmistakably Saturn was a detailed, pixelated representation of its moon, Enceladus. And next to this moon was a tiny, blinking icon. The implication was paralyzing. The signal was not just acknowledging our message, it was highlighting a specific location within our own celestial backyard, suggesting a knowledge of our system that was not just general but precise and current. This moved the conversation from the abstract realm of interstellar hellos to the immediate, visceral reality of a presence that knows our neighborhood intimately. This event immediately plunges us into a whirlpool of ethical and existential questions that the scientific community has debated for decades. The core of the controversy is the active SETI paradox. For years, prominent scientists like Stephen Hawking warned against precisely this kind of initiative, comparing it to the foolishness of shouting into a dark and unknown jungle. We have no idea who or what might be out there, and their intentions, morality, and biology could be completely alien to our own. By announcing our presence and location so loudly, have we potentially invited a calamity? Proponents of active SETI argue that any civilization capable of interstellar travel and communication would necessarily have overcome the self-destructive tendencies that plague humanity and would likely be peaceful or at least benign. They see the response as a moment of supreme triumph, the first step toward joining a galactic community. The critics, however, see the blinking icon near Enceladus not as a friendly wave, but as a potential claim marker or a target designation, and they view Project Mirage as an act of unparalleled naivety that may have jeopardized all of humanity. Beyond the fear of invasion lies a deeper, more philosophical terror, the implications of the response time. The Lacerta cloud is 900 light-years away. Even traveling at the speed of light, our message should have taken 900 years to arrive, and any reply another 900 years to return. The fact that a response came in weeks, not millennia, suggests one of two equally universe-shattering possibilities. The first is that the respondents are not in the dust cloud at all, but are much, much closer, perhaps even within our own solar system, using the cloud as a symbolic return address or a relay point. The second, and even more profound, possibility is that they have mastered a form of communication that is not bound by the speed of light. This would mean our understanding of physics, the absolute limit of cosmic velocity, is fundamentally wrong. Either scenario forces a Copernican-level revolution in our self-perception, suggesting we are not the isolated masters of our local space that we believed ourselves to be. The structure of the potential reply adds another layer of complexity. It wasn't a simple hello, but a mirrored, corrected version of our own package. This suggests a civilization that learns and communicates through rapid, perfect mimicry and refinement, a form of intelligence that might be more synthetic than biological. The response feels like the work of a powerful, analytical system, perhaps an ancient AI designed for first contact. It received our data, processed it instantly, and sent back a version that demonstrated not just comprehension but superior knowledge. The signal that changes based on what we transmit is perhaps the most significant and frightening discovery in human history because it transforms the universe from a silent, impersonal expanse into a realm that appears to be not only inhabited but acutely aware and now unmistakably responsive. The idea that we might be in an active, real-time conversation with an intelligence that knows our solar system intimately is a staggering proposition. But our 20th mystery suggests an even deeper layer of connection, one that binds together the very fabric of spacetime itself. This signal, detected from a quiescent dust cloud in the Vela constellation, did not announce itself with a complex image or a predictive pattern. Instead, its significance was only realized months after its detection, during a routine data review that coincided with a major announcement from the LIGO and Virgo gravitational wave observatories. Researchers noticed something that should have been impossible: the amplitude of the radio signal, its rises and falls in intensity over a period of several minutes, was a perfect match for the waveform of a gravitational wave event catalogued as originating from the merger of two neutron stars. The radio whisper from the Vela dust cloud and the spacetime ripple from the cosmic collision were, for a brief window, the same song played on two different instruments. The gravitational wave signal itself was a textbook event. It had the characteristic chirp, a rapid increase in frequency and amplitude as the two ultradense stars spiraled inward and finally collided, an event that happened over 100 million light-years away. The radio signal, however, came from a dust cloud within our own galaxy, a mere 1,500 light-years from Earth. According to our current understanding of physics, this makes no sense. Gravitational waves and electromagnetic waves are fundamentally different phenomena. Gravitational waves are ripples in the fabric of spacetime itself, traveling at the speed of light but interacting very weakly with matter. Radio waves are oscillations of electric and magnetic fields within spacetime. There is no known mechanism by which a gravitational wave passing through a dust cloud could directly generate a radio signal that perfectly mimics its own complex waveform. It would be like a sound wave passing through a brick wall and causing the bricks to glow with a light pattern that exactly matches the sound's frequency. This paradox has forced physicists to consider radical new theories that attempt to bridge the chasm between gravity and electromagnetism. One leading hypothesis involves a speculative concept known as the gravitational photon. In this unproven framework, under certain extreme conditions, gravitational waves could theoretically interact with the quantum vacuum, the seething sea of virtual particles that fills empty space, and generate photons, particles of light. For this to happen in a way that precisely copies the waveform, the dust cloud would need to possess a very specific and unlikely configuration of magnetic fields and particle density, acting as a perfect transducer. While mathematically possible, the chances of a natural cloud aligning in such a perfect way to produce this effect are astronomically low, making this explanation a frontier of theoretical physics rather than a settled matter. A second, even more exotic possibility is that both signals, the gravitational wave and the radio wave, were not the primary events but secondary effects of a single, deeper cause. Imagine a technology so advanced it doesn't just use the universe, it manipulates its underlying rules. A civilization capable of engineering neutron star mergers, or perhaps simulating them with energies we can't comprehend, might use the resulting gravitational wave as a carrier signal. The synchronized radio emission from a nearby dust cloud could then act as a tag or a beacon, drawing the attention of any observers sophisticated enough to detect both phenomena. In this scenario, the dust cloud might be pre-equipped with some form of technology that is triggered by the specific vibration of space-time from the merger, instantly converting that energy into a matching radio broadcast. This would be a display of power and coordination on a literally cosmic scale, suggesting an intelligence that can orchestrate events across star systems and manipulate the most fundamental forces as a form of communication. The implications of such a coordinated signal are profound. It suggests that if there is intelligence out there, its mode of communication may not be limited to the narrow radio window we've been searching. They might be using the universe itself as a medium, encoding messages in the collisions of stars, the vibrations of space-time, and the light from nebulae, all working in concert. The gravitational wave correlate forces us to expand our definition of a signal beyond simple radio transmissions. It hints at a language written not in words or pictures, but in the choreographed dance of energy and matter, a language that requires us to listen with all of our instruments at once to even begin to understand the conversation. Imagine a signal that begins not as a message but as a student. Our 21st mystery takes us to the outskirts of the North America Nebula, a vast, star-forming region shaped like the continent it's named for. For years, a faint, broad-spectrum radio hum from this area was dismissed as background static, the kind of unremarkable emission that fills the spaces between stars. It was only when a long-term analysis project compared data spanning more than a decade that a startling trend emerged. The signal was changing. Its chaotic noise was gradually resolving, becoming more structured. It began to develop distinct peaks and troughs in its spectrum, and then something even more specific happened. It started to exhibit modulation schemes eerily similar to those used in early human digital broadcast. It was as if the signal was learning, adapting its form over time to mirror the very technologies we use to fill the airwaves around Earth. The progression was methodical. Initially, the signal's modulation resembled simple amplitude modulation, or AM radio, the first technology we used for widespread broadcasting in the 20th century. Then, years later, it began to incorporate elements of frequency modulation, or FM, the cleaner, more advanced standard that followed. Most recently, analysis has detected patterns that suggest a rudimentary form of packet switching, the fundamental principle behind the Internet, where data is broken into small chunks and sent independently before being reassembled. This chronological mimicry is what makes the signal so deeply unsettling. It isn't just transmitting, it appears to be replaying our own technological evolution back to us, but in a compressed timeline, as if it has been auditing our radio and television leakage for decades and is now attempting to open a dialogue using a language it has deduced we will understand. This behavior points directly to the concept of a von Neumann-style monitoring probe, but with a terrifying twist. Instead of a passive observer merely collecting data, this would be an active listener, an intelligent system designed for long-term surveillance. Such a probe, parked in a nearby nebula, would have had a front-row seat to the development of human civilization since we first began broadcasting radio waves into space over a century ago. It would have received our earliest radio dramas, our television signals, our military radar, and now our digital internet traffic. All of this information would have been stored and analyzed, allowing the probe's AI to build a comprehensive model of our communication methods, our culture, and even our technological capabilities. The signal we are now detecting could be its first attempt at making contact, using a synthesized version of our own historical broadcast standards as a form of universal handshake. The implications of this are profound and double-edged. On one hand, this could be an incredibly thoughtful and benevolent act. An advanced intelligence might believe that the most effective way to communicate is to use a familiar format, reducing the potential for misunderstanding. It would be the cosmic equivalent of a traveler learning the local language before attempting to speak. The gradual pedagogical progression of the signal, starting with simple AM and moving to more complex schemes, could even be interpreted as a tutorial designed to gently introduce us to the concept of interstellar dialogue by beginning with principles we already know. However, the alternate interpretation is far more ominous. This learning behavior is also the hallmark of a reconnaissance system. Before any first contact or any potential conflict, a sophisticated entity would want to gather as much intelligence as possible. By studying our leaked signals, the probe would have learned not just our languages, but also our politics, our history of warfare, our social divisions, and our technological vulnerabilities. The fact that it is now attempting to communicate could signal that its data collection phase is complete. The seemingly friendly act of mirroring our technology could be a ruse, a way to establish a communication channel that it knows we will be able to receive and trust, only to then deliver an ultimatum, a warning, or a deception. The signal's evolution from noise into a reflection of ourselves is a powerful mirror, and what we see staring back could be either a welcoming smile or a predator learning to wear a familiar face. After confronting signals that mimic our technology and coordinate with cosmic collisions, we now venture into a realm of profound silence, where a mystery emerges from a place we least expected. Scattered throughout the galaxy are dust clouds that have, for all intents and purposes, reached the end of their life cycle. These are not the vibrant, glowing nurseries of the Orion or Carina nebulae. They are cold, dark, and diffuse, having long since dissipated their reservoirs of gas or been stripped of the gravitational potential needed to collapse into new stars. To astronomers, these are considered dead clouds, cosmic graveyards where the energetic processes of birth have ceased, leaving behind only a faint, cold haze of particulate matter. It was from one such cloud in the constellation of Cepheus that a powerful, complex signal was detected, a discovery that fundamentally challenges our understanding of where signs of activity and perhaps even intelligence can be found. The initial detection was met with widespread skepticism, primarily because the signal's characteristics were at odds with its environment. This was not a simple, broad-spectrum whisper of thermal emission. It was a structured, narrowband radio transmission, pulsing with an intricate rhythm that suggested a sophisticated source. The immediate assumption was that the signal's origin point had been misidentified, that it must be coming from a bright object behind the cloud, its light simply filtering through the tenuous dust. Yet, painstaking parallax measurements and multi-wavelength observations confirmed the impossible. The signal's epicenter was located deep within the heart of the cloud itself. Spectroscopic analysis of the cloud only deepened the mystery. The dust grains were measured to be only a few degrees above absolute zero, and the cloud's density was so low that collisions between particles were incredibly rare events. This is an environment devoid of the energetic turmoil needed to power natural radio sources like masers or plasma oscillations. It is the cosmic equivalent of a ghost town, silent and still for eons, making the presence of a powerful, organized signal as baffling as hearing a symphony orchestra playing in a vacuum. This paradox forces us to reconsider one of the foundational assumptions in the search for extraterrestrial intelligence, that we should focus our efforts on active star systems. The logic has always been that life, and by extension technology, requires energy, and the most abundant sources of energy are found around stars. A dead cloud offers nothing. No solar power, no geothermal energy from planets, no raw materials for fusion. So, what could possibly be operating there? One compelling line of thought points to the possibility of a dormant artifact. Imagine a probe or a monitoring station launched by a civilization millennia ago, sent to observe this region when it was still a bustling stellar nursery. Over time, as the cloud dissipated and the stars it formed drifted away, the artifact's primary mission would have ended. But instead of shutting down, it could have entered an ultra-low power state, a form of hibernation designed to preserve its systems for an astronomical timescale. Its power source might be a long-lasting radioisotope thermoelectric generator, or something far more advanced, like a device that taps into the quantum fluctuations of the vacuum itself. The signal we detect could be a periodic heartbeat broadcast, a status check emitted once every century to announce that it is still functional, waiting in the silence for a command that may never come. This concept of dormancy leads to an even more profound idea, that the cloud itself is not dead but is being used as a camouflage. A technologically advanced civilization, perhaps one that wishes to remain hidden, might choose the most inconspicuous location imaginable for its long-term installations. A bright, active nebula would be flooded with radiation and constantly scanned by astronomers. A cold, dark, and ostensibly dead cloud, however, is the perfect place to hide. No one would think to look there. The signal's power might be a calculated risk, its creators confident that the sheer improbability of its location would cause any detection to be dismissed as an error for decades, just as it initially was. In this scenario, the cloud is not a graveyard but a secure vault, and the signal is a carefully managed leak, intended only for those who know exactly where and how to listen. Beyond the artificial explanations, theoretical physicists have proposed a truly exotic natural phenomenon that could account for the signal. In the ultra-cold, ultra-quiet environment of a dead cloud, a quantum mechanical effect known as macroscopic quantum coherence might become possible. At temperatures near absolute zero, the random thermal jostling of atoms nearly ceases. In this pristine state, it is theorized that a vast collection of dust grains, if they possess a particular crystalline structure or magnetic property, could become entangled. This means their quantum states would be linked across the entire cloud, acting as a single macroscopic quantum object. If this collective were then perturbed by a passing cosmic ray or a subtle gravitational wave, it could release its energy not as random heat, but as a coherent emission of radio waves, a single, synchronized pulse from trillions of particles acting as one. While entirely theoretical, this would be a previously unobserved state of matter, a natural laser or maser operating on a scale we can barely imagine, born from the profound peace of a cosmic void. The signal from the dead cloud ultimately confronts us with a choice between two breathtaking possibilities. Either we are hearing the faint, persistent heartbeat of a machine left behind by explorers from another world, or we are witnessing an entirely new form of physics emerging from the deepest cold and quiet the universe has to offer. After exploring the eerie silence of a dead cloud, our journey takes us to the most violent and extreme environment in our entire galaxy, the chaotic heart of the Milky Way itself. Nestled within the swirling maelstrom of gas and dust that surrounds the supermassive black hole Sagittarius A, astronomers have detected a pair of signals so peculiar they demand to be considered together. Signals 23 and 24 originate from two separate dust clouds positioned on opposite sides of the galactic center, and they share one extraordinary telltale feature: an identical and extreme degree of polarization. This characteristic is so rare and specific that it acts like a fingerprint, pointing directly to the unique physics at play in this formidable region of space. To understand why this polarization is so significant, picture an ordinary beam of light or radio waves. The waves vibrate in all directions perpendicular to their path, like a wiggling rope shaken randomly up and down and side to side. Polarization is the process of filtering those waves so they vibrate in only one specific plane. You experience this with polarized sunglasses, which cut the glare from horizontal reflections off water or asphalt. In the cosmos, natural processes can create polarized emissions, but they are usually weak or messy. The polarization detected from these two clouds, however, is nearly 100% perfect and most astonishingly identical in its orientation. It's as if both signals pass through the exact same, perfectly aligned cosmic filter, a coincidence that is incredibly difficult to attribute to random chance in such a turbulent environment. The immediate vicinity of a supermassive black hole is a realm of almost unimaginable forces. The gravitational pull is so intense that it whips stars and gas clouds into frenzied orbits at a significant fraction of the speed of light. This motion generates powerful magnetic fields that are stretched and twisted into colossal dynamic structures. One compelling natural explanation for the polarized pair is that these very magnetic fields are the cause. As electrons are accelerated to near-light speeds along the powerful, ordered magnetic field lines funneling into Sagittarius A, they can emit a type of radiation known as synchrotron radiation. This emission is naturally highly polarized, with the orientation of the polarization directly revealing the direction of the magnetic field. If both dust clouds are illuminated by the same coherent, large-scale magnetic structure emanating from the black hole, they could indeed produce signals with identical polarization. It would be a spectacular, if violent, natural lighthouse, its beam defined not by optics but by the invisible architecture of magnetism on a galactic scale. However, the sheer perfection of the match gives pause. The galactic center is not a clean, orderly place. It is a chaotic soup of colliding winds from massive stars, shock waves from supernova, and the general tumult of matter spiraling toward its doom. For a magnetic field to maintain such a consistent orientation across light years of this turmoil, to imprint an identical signature on two separate clouds is a tall order. This opens the door to a more technological interpretation, that the polarization is the signature of a directed energy beam. Imagine a civilization that has established itself near the most energetic engine in the galaxy. The supermassive black hole could serve as an ultimate power source, and beaming energy from it would be a tremendous technological feat. A powerful, coherent beam, like that from an optical laser or its radio equivalent, a maser, is inherently highly polarized. If such a beam were being used for communication or propulsion, and it happened to sweep across these two dust clouds, it would make them glow with the same polarized light, like two streetlights illuminated by the same passing car's headlights. The purpose of such a beam is a matter of breathtaking speculation. It could be a form of interstellar infrastructure, a power transmission line feeding energy to remote outposts or ships. Alternatively, it could be a communication channel of unimaginable bandwidth. The extreme energies available at the galactic center would allow for a signal so powerful it could be detected across the universe, and the precise polarization could be a way to encode information, making the signal resistant to interference from the background noise of the galaxy. The dust clouds themselves might be incidental, simply the nearest material for the beam to interact with and make its presence known to distant observers like us. The polarized pair from the galactic center forces us to contemplate a possibility far beyond solitary probes or listening posts, that we might be seeing the indirect evidence of a Kardashev Type 2 or even Type 3 civilization, one that has learned to harness the power of stars and black holes, and whose activities are written in the fundamental properties of light itself across the vast core of the Milky Way. And so we arrive at the final and perhaps most emotionally resonant mystery on our list, a signal that offered a fleeting glimpse of profound understanding before vanishing into the cosmic background, leaving behind a haunting sense of loss. Signal 25 was detected emanating from the Rosette Nebula, a beautiful flower-like cloud of gas and dust where new stars are constantly being born. Unlike the sudden bursts or erratic flickering we've encountered, this signal appeared quietly and then began a steady, deliberate crescendo. Over the initial weeks of observation, it didn't just grow louder, it grew richer, its structure evolving from a simple carrier wave into a symphony of modulated frequencies. It was as if we were slowly turning a dial on a cosmic radio, and after centuries of static, we were finally tuning into a clear and ever more complex channel, a broadcast that seemed to promise a revelation. The scientific community watched with a mixture of exhilaration and anxiety. Every day brought new data, revealing intricate layers within the signal. Sub-channels appeared, suggesting multiple streams of information being transmitted simultaneously. The complexity was staggering, far exceeding anything observed in a natural source and dwarfing the most sophisticated human broadcast. It felt like we were on the verge of a breakthrough, that if we could just gather a few more weeks or months of data, we might finally have the key to decoding a message from the stars. Telescopes around the world were prioritized to focus on the Rosette Nebula, creating a global network dedicated to capturing every last nuance of this extraordinary transmission. We were leaning in, listening with bated breath, convinced we were witnessing the beginning of a new chapter in human history. Then the unthinkable happened. The signal peaked, and instead of stabilizing, it began to fade. It was a gradual process, not an abrupt cessation. The complex modulation simplified, the sub-channels dropped away one by one, and the overall intensity began a slow, inexorable decline. It was a reverse of the process we had first observed, as if the transmitter was slowly shutting down its systems, or the universe itself was turning the dial back toward static. For months, astronomers tracked the fading whisper, their hopes diminishing with each passing day. They tried everything, boosting receiver sensitivity, employing new decoding algorithms, searching for the signal in adjacent frequency bands, but it was like trying to hold water in your hand. The signal continued to weaken until, finally, it dropped below the threshold of detection and was gone, leaving only the ancient, impersonal hiss of the universe. This heartbreaking event draws a powerful parallel to one of history's greatest intellectual tragedies, the destruction of the Library of Alexandria. That legendary institution was said to hold a vast fraction of the ancient world's knowledge, a collection of scrolls containing works of philosophy, science, and literature that are now lost to us forever. We know it existed, we know it was profound, but we are left with only fragments and legends, forever wondering what insights were consumed by the flames. Signal 25 is our cosmic library of Alexandria. We were granted a brief, glorious look at a repository of information of unimaginable scope, only to have the door shut before we could truly step inside. The feeling is not just one of mystery, but of poignant loss, the agony of a missed opportunity that might not come again. This experience forces us to confront two deeply unsettling possibilities. The first is that we were simply too late. The signal may have been a one-time event, the final, dying transmission of a civilization that had exhausted itself, a broadcast that had been traveling for millennia and we only caught its tail end. In this scenario, the fading wasn't a shutdown, but the literal end of the power source, the last gasp of a cosmic beacon that had finally burned out. We tuned in for the final chapter of a story that had begun long before humanity walked the earth, and the silence that followed is permanent. The second possibility is even more torturous, that we missed our window. What if the signal was part of a cyclical or repeating broadcast, and the period of clarity we witnessed was just a fleeting alignment? Perhaps the relative motion of the stars or the shifting densities within the nebula created a temporary corridor of clear transmission that lasted for only a few months. The signal might still be out there, but now it's too distorted by interference for us to detect, or it has shifted to a frequency we aren't monitoring. It could be broadcasting on a cycle of 1,000 years, and we happen to be listening during the briefest of peaks. This idea transforms the event from a tragedy into a test of cosmic patience, a lesson that the universe operates on timescales that humble human ambition. The signal that faded as we listened serves as the ultimate conclusion to our journey through these 25 mysteries. It reminds us that the cosmos is under no obligation to reveal its secrets on our schedule, and that the search for understanding is as much about grappling with silence as it is about decoding the whispers. This journey through 25 of the cosmos's most baffling whispers brings us face to face with a question that has haunted humanity since we first looked up at the stars. If the universe is so vast and so old, where is everybody? This is the essence of the Fermi paradox, the stark contradiction between the high probability of extraterrestrial life and the utter lack of evidence for it. One of the most compelling answers to this paradox is the concept of the Great Filter, a hypothetical barrier or challenge so difficult that it prevents almost all life from advancing to the stage of interstellar civilization. The existence of these unexplained signals forces us to ask a terrifying question about this filter. Does it lie in our past, meaning we are the rare ones who have already overcome it? Or does it lie ominously in our future, and these signals are the faint, fading echoes of those who failed? Consider the signals that suggest advanced, enduring technology. The Scorpius-Centaurus triangulation, with its perfect geometric alignment spanning 130 light-years, implies a civilization capable of engineering on a galactic scale. The signal hidden within the Crab Nebula's pulsar suggests a mastery of energy that borders on the magical, using stars as billboards. If such beings exist or existed, they clearly passed through whatever great filter their era presented. This line of thinking offers a hopeful, if humbling, perspective. The great filter is behind us, perhaps the incredible series of chance events that led from non-living chemistry to simple life, and then from single-celled organisms to intelligent, technological beings, is the universe's rarest fluke. We might be alone, not because space is empty, but because we are the first, or one of the very few, to have made it this far. In this scenario, these signals are not active communications, they are archaeological relics. We are not listening to contemporaries, but exploring the cosmic ruins of civilizations that rose and fell billions of years ago, their automated beacons still dutifully broadcasting into the silence long after their creators are gone. We are the new kids on the block, wandering through a galaxy of ghosts, yet other signals paint a far more cautionary picture, one where the filter looms large in our future. The sudden, permanent silence of the signal from Lyra's veil reads like a cosmic tragedy, a conversation cut short by catastrophe. The predictive signal from Cygnus, which seemed to warn of our own sun's flares, could be interpreted as evidence of a universe fraught with existential dangers that advanced civilizations learned to monitor. Dangers we are only beginning to understand. Most chilling of all is the response to Project Mirage, the signal that seemed to answer in real time and pinpoint a location in our own solar system. This scenario suggests the Great Filter is not a natural obstacle, but a technological or social one. It might be the point where a civilization, upon achieving the power for interstellar communication or travel, inevitably self-destructs through war, ecological collapse, or a runaway artificial intelligence. Alternatively, the filter could be a predatory universe where any civilization bold enough to announce its presence is quickly silenced by a far older, more advanced, and perhaps hostile intelligence. The fact that so many of the signals we detect are transient, mysterious, and often suggestive of isolation or decay could be seen as evidence that longevity is the universe's ultimate challenge. The great filter, in this view, is the wall that separates short-lived, noisy species from the quiet, enduring ones, if any enduring ones exist at all. The debate between these two possibilities is not merely academic. It is a lens through which we must view our own future. If the filter is behind us, our mission is one of exploration and discovery, tasked with uncovering the galaxy's ancient history. But if the filter is ahead, then every signal we detect carries a dual meaning. It is both a tantalizing clue and a potential warning. The flickering beacon in Taurus might not be a broken machine, but a monument to a civilization that failed to maintain its technology over geological time. The signal that learned our own broadcast methods might not be a friendly student, but a reconnaissance tool assessing a new candidate for the filter. This interpretation imbues the search with a profound gravity. Our efforts to decode these cosmic whispers are not just a quest for knowledge. They are a race to understand the rules of a universe that may be far more dangerous than we ever imagined, hoping to learn from the mistakes of those who once shone as brightly as we do now, before they were silently returned to the dust from which they came. But how do we actually hear these whispers? The technology required to detect such faint, fleeting signals from across the galaxy is a marvel of human ingenuity in its own right. It begins with colossal ears pointed at the sky, radio telescopes. These are not the optical telescopes you might picture with a lens and an eyepiece. They are massive parabolic dishes, some as large as a football field, designed to act as giant mirrors for radio waves. When these long wavelength, low-energy photons from space rain down on Earth, these dishes capture and focus them onto a receiver, much like a satellite TV dish on your roof, but operating on a cosmic scale. The sheer size of the dish is crucial. It determines the telescope's sensitivity, its ability to gather enough of these sparse radio photons to form a detectable signal out of the background hiss of the universe. The legendary Arecibo dish in Puerto Rico before its collapse was a prime example. Its 305-meter diameter bowl carved into a natural limestone sinkhole, listening to the cosmos for decades. Yet a single dish, no matter how large, has its limits. Its resolution, its ability to pinpoint fine details in the sky is constrained by its diameter. To see the equivalent of a cosmic postage stamp from thousands of light years away, you need a telescope of impossible size. This is where the true magic of modern astronomy comes into play: interferometry. Instead of building one impossibly large dish, we build an array of many smaller dishes spread out over a vast area. By combining the signals from these separate telescopes and using the precise timing differences as the waves arrive at each one, astronomers can create a virtual telescope with a diameter equal to the greatest distance between the dishes. It's like creating a giant eye whose pupil is the size of an entire continent. The Very Large Array in New Mexico, with its 27 iconic antennas arranged in a Y-shaped pattern that can be moved along railroad tracks, is a stunning example, its resolving power allowing it to see details finer than the Hubble Space Telescope, but at radio wavelength. The next great leap in this endeavor is already underway: the Square Kilometer Array, or SCAR. This is not just an upgrade, it is a revolution. As the name suggests, the goal is to build a collecting area for radio waves that totals approximately 1 square kilometer, but distributed across thousands of individual antennas. The project is international in scope, with core sites in the remote deserts of South Africa and Western Australia, chosen for their profound radio silence, far from the polluting buzz of human civilization. When fully operational, the SKA will be so sensitive that it could detect an airport radar on a planet orbiting a star tens of light years away. It will survey the sky 10,000 times faster than any current system, mapping the entire visible universe in unprecedented detail and monitoring vast swaths of space continuously for the kind of transient, unexplained signals we've been exploring. The SKA won't just be looking for one signal at a time. It will be listening to the entire cosmic symphony simultaneously, with the processing power to pick out every single instrument, every subtle melody, and every faint discordant note. This incredible sensitivity, however, creates its own greatest challenge, the cacophony of noise. Distinguishing a cosmic whisper from the background static is like trying to hear a single conversation in a crowded, roaring stadium. The interference comes from two main sources. First, and most frustratingly, are our own creations. Our planet is drowning in a sea of artificial radio waves, television broadcasts, satellite communications, mobile phone networks, and even the spark plugs in car engines. These signals are billions of times stronger than the faint whispers from interstellar dust clouds. Astronomers must engage in a constant battle, using sophisticated algorithms to identify and subtract these human-made fingerprints from their data, a process that requires knowing the precise location and frequency of every terrestrial transmitter. It's a delicate digital surgery, cutting away the noise without accidentally excising the very signal they are searching for. The second source of noise is the universe itself. Space is not silent. It crackles with a remnant echo of the Big Bang, the cosmic microwave background. It hums with the synchrotron radiation from electrons spiraling around magnetic fields in our own galaxy. Distant quasars roar, and the constant particle wind from the sun creates a hiss of its own. Filtering out this natural cosmic static requires an intimate understanding of astrophysics. Scientists create complex models predicting what the background noise should look like at a given time and frequency, and then subtract that model from the observed data. What remains, the anomalies, are the treasures. This is how signals like the one hidden within the Crab pulsar's emissions are found, not by listening for a loud signal, but by meticulously modeling the loud, predictable signal and then examining the subtle imperfections left behind. The technology of listening, therefore, is not just about building bigger ears. It is about building smarter brain supercomputers and algorithms capable of sifting through an ocean of data to find the one drop that is truly different, the faint, enigmatic whisper that just might change everything we know. All of these incredible signals, from the faint whispers in the Boötes Void to the coordinated symphony near the galactic center, represent clues gathered with the technology of today and yesterday. But the search is accelerating at a breathtaking pace, propelled by a new generation of tools that promise to peer deeper into the cosmic dust than ever before. The next chapter in this grand investigation is already being written, not just by bigger telescopes, but by smarter, more sensitive, and more interconnected observatories that will transform our understanding of these enigmatic regions. The coming decades will see us move from simply detecting anomalies to actively probing the very environments from which they spring. One of the most powerful new allies in this quest is the James Webb Space Telescope. While often celebrated for its stunning images of distant galaxies, Webb's capabilities are perhaps even more revolutionary for studying the local universe, specifically the chemistry within star-forming nebulae and dust clouds. Its infrared eyes are perfectly suited for this task. Visible light is easily scattered and absorbed by dust, which is why these clouds appear as dark patches in the night sky. But infrared light, with its longer wavelengths, can pass through the dust almost unimpeded, like a heat vision camera seeing through smoke. Webb can do more than just see through the veil. It can perform a detailed chemical analysis of the material inside. By studying the spectra of the light that filters through, it can identify the fingerprints of complex organic molecules, the building blocks of life floating within these cosmic nurseries. This allows us to answer a fundamental question: are these clouds merely inert collections of dust, or are they vibrant chemical factories? If we begin to find clouds with unusually complex chemistry, or even chemical signatures that suggest artificial manipulation, such as an imbalance of certain isotopes or the presence of molecules not expected to form naturally, it could provide a crucial context for any strange signals we detect. A mysterious radio transmission from a cloud that also contains a bizarre chemical makeup would become a far more compelling target. On the ground, the search is being revolutionized by artificial intelligence. The sheer volume of data pouring in from telescopes like the Square Kilometre Array will be so immense that no team of human researchers could ever hope to sift through it. This is where advanced machine learning algorithms come in. Unlike traditional software that follows strict rules, these AIs can be trained to recognize subtle patterns that human eyes might miss. They can learn the unique sound of every known natural phenomenon, from pulsars to stellar flares to radiation from distant quasars, and then flag any signal that doesn't fit the established patterns. This goes far beyond simply looking for narrowband transmissions. An AI could detect a signal that is artificially disguised to look natural, one that changes in a complex but non-random way, or one that exhibits the kind of long-term memory we saw in the Rho Ophiuchus signal. These systems won't get tired, they won't suffer from apophenia, and they can process lifetimes of data in a matter of hours, turning the cosmic haystack into a searchable database and dramatically increasing our chances of finding the needle. The ultimate goal, of course, is a confirmed discovery, but what would that moment actually mean for humanity? The societal impact would be seismic, dwarfing any event in recorded history. The initial scientific revolution would be profound, answering the ancient question of whether we are alone and instantly granting us a comparative biology and sociology. But the deeper shockwaves would ripple through every facet of our culture. Philosophically and religiously, it would force a fundamental re-evaluation of humanity's place in the universe. Some faiths might incorporate the discovery into their cosmology, seeing it as a validation of a creation filled with life. Others might face a crisis as their doctrines, which place humanity at the center of a divine plan, are challenged. This would not necessarily lead to collapse, but to a period of intense theological and philosophical reinterpretation, a new enlightenment grappling with our status as just one intelligent species among many. On a practical level, the knowledge that advanced intelligence is possible and that it can endure long enough to bridge the stars could have a unifying effect on our own fractured planet. The classic thought experiment suggests that a common, external challenge can bring humanity together. The confirmation of an alien civilization, even a distant and silent one, would represent the ultimate external context. It could potentially catalyze global cooperation on a scale never before seen, as we shift from competing national interests to a shared human identity faced with the vastness of a populated cosmos. The drive to understand the message, to learn their technology, and to ensure our own survival and place in the galactic community could fuel a new age of scientific and cultural aspiration. The future of the search is not just about building better tools, it is about preparing ourselves for the moment those tools finally succeed, opening a door to a universe that is stranger, more connected, and far more wondrous than we have ever dared to imagine. So after this journey across the galaxy, what are we left with? 25 distinct whispers, each a singular enigma, yet together they weave a tapestry that reveals a profound truth about our place in the cosmos. From the faint, repeating pulses echoing from the unimaginable emptiness of the Boötes Void, to the coordinated symphony of signals around the supermassive black hole at our galactic center, these are not random anomalies. They are persistent, structured, and deeply challenging. They defy simple categorization, stubbornly resisting our best attempts to explain them away as mere pulsars, masers, or instrumental glitches. The common thread running through all of them is not a specific frequency or a pattern, but the very fact of their mystery, a consistent reminder of the limits of our current knowledge and the boundless potential for discovery that lies just beyond it. This represents a fundamental shift in our cosmic perspective. For centuries, those dark patches in the Milky Way, the interstellar dust clouds, were seen as nothing more than obscuring veils. They were the fog that hid the brilliant stars behind them, obstacles for astronomers to peer through or work around. But now, thanks to these unexplained signals, we are forced to see them in a new light. They are not empty voids or simple curtains, they are dynamic frontiers. They are the nurseries of stars, the repositories of complex chemistry, and just possibly the hiding places of phenomena we cannot yet imagine, whether they be exotic new laws of physics, the ruins of ancient civilizations, or the active outposts of intelligence so advanced their operations are indistinguishable from nature itself. The dust is no longer an obstacle, it has become the destination, and this is why the search must continue. The next great discovery might not come from a dramatic, obvious beacon, but from the subtle, patient analysis of data we have already collected. It might be hidden in the quiet spaces between the beats of a known pulsar, or in the slight, statistical imperfections of the cosmic microwave background. It requires our continued curiosity, our investment in powerful new instruments like the Square Kilometre Array, and our willingness to question our most fundamental assumptions. The universe is under no obligation to make itself easily understandable to us, and that is precisely what makes the pursuit so thrilling. The greatest secret might be waiting in the very next data stream, a whisper so faint we have simply not yet learned how to listen for it. So the next time you find yourself under a clear, dark sky, take a moment to look up at the Milky Way. Let your gaze not just settle on the bright, brilliant stars, but on the dark rivers and bays that flow between them. Those are not empty spaces, they are the cosmic dust clouds, and within their shadows the universe is murmuring. We have heard 25 of its most compelling secrets, but for every one we've captured, 1,000 more likely remain unheard. The conversation is just beginning. We want to hear which of these signals captured your imagination the most. Was it the haunting, unanswered call from Lyra's veil, the terrifyingly responsive message from Project Mirage, or the geometric perfection of the Scorpius-Centaurus triangle? Share your thoughts in the comments below, and let's keep wondering together about what other secrets the dust